Surendra Kiran Kole, did you respond?
Yes, sir.
Okay. So now, having gone through one cycle of everything, we come back to have a look at it again and again. It will be good for you to now start reading the textbooks so that we proceed. Especially after a few more classes, we will be able to just hold the line a little. We will, sorry. After a few more classes, we will be able to fully sync up, and you'll see that we have learned a lot of things which by doing unknown problems. So our method, if you take a look at the method, our function, which is a recursive definition, has got these 5 components. There is a base condition. There is a decomposition function. Then there is a recursive call. And then the results of the recursive call are composed. And the composed result is returned. Let us say in the coins problem, using the inclusion exclusion principle, we know our base conditions. Utkarsh Avasthi, what are our base conditions? Vanshika Sahu, Yerawar Rushi Girish,
Yes, sir.
what are our base conditions in the coins problem?
If the z equal to 0, we need
Correct.
to return.
Ah,
Uh, if z is negative, we need to return infinite value.
very good.
Uh, if all the coins are, I mean, there is no coin in the set, then also we need to return.
Hmm.
Where we have to check whether z is equal to
Good, good.
0
So
or
we
not.
know, very good, very good. Now, somebody else, Shayon Laik, are you there?
Yes, sir.
What are my decomposition functions in
Sir,
the coins?
we are choosing a we are either choosing a coin or we are not choosing a coin.
Correct, correct, correct. And then we make a recursive call.
Yes, sir.
Correct?
Yes, sir.
Yeah.
Yes, sir.
And Shivam Agarwal, are you there? You are never there. Shashi Ranjan,
Yes, sir.
what is my decomposition after having got that solution? What is my recomposition function? What is my recomposition function?
Uh,
If I've got solution 1 and solution 2, what do I do with them? What was I doing in my algorithm? Anybody else would like to suggest what is my recomposition function?
So taking the
minimum.
minimum.
Minimum. My recomposition function is minimum. So with these as the structure of my recursive definition, it looks like this. There is a decomposition, then it is recursively called. Sometimes you reach a base condition, sometimes you reach a recursive condition. The base conditions are then recomposed and the final recomposition is obtained. This is how it looks like. And in order to, our purpose is to examine this structure and propose efficient algorithms. Are there identical subproblems? If there are 5 ways to split it, which is the best way to do that? How to recompose, how to make sure that I don't need to do unnecessary things, etc. And we have done all our problems. And we just saw that, it leads to all these algorithms that we talk about. So now the divide and conquer method is mainly concerned about optimizing the split. That means from the recursive condition, which is the best way to split the set. When we did only max, we found all splits are identical. When we did max min, which split was found to be good?
n minus 2.
2 and minus 2. Yeah. And when we did the max second max, we not only did the split that way, that we balanced everybody. First, we did them pairwise, and then we also developed a data structure. So divide and conquer method in typically is concerned about how to optimally break up the problem among the 5 options that you had, which means that it is mostly concerned with an efficient recursive decomposition. So in order to do that, we will now pick up a set of problems. The first problem that we pick up is an unordered set or a list. So I have a list. So we'll pick up the problem of searching and sorting. For the time being, we'll pick up the problems of searching and sorting. And our first problem is search an unordered set for an element S. This is an unordered set. This is an element S. It will return yes if element S is in U. It will return no if element S is not in U. Simple problem. How do I solve this problem? By our method.
So we can use, we can check the first element and then recursively decompose. No, it's actually iterative.
This is identical to one of the problems we have solved.
Minimum, finding minimum of the list.
Yeah, so you can break it up. What is our mechanism? Break U into 2 non-empty.
Non-empty lists.
Search S in U, U1 and U2. Search S in U1. What is my recomposition function?
Minimum of both searching.
Kaha minimum? This is an unordered set. Some names are there, alphabets are there, something is there. You're just searching. We don't even know whether the elements of U can have an ordering or not.
So if any of the decomposed return yes, then we return yes. Else
Yeah, so
no.
it's an OR.
An OR.
OR recomposition is an OR.
Yes, sir.
So we break it up into U1 and U2 and search U1. If I get it, my problem is solved. Otherwise, I search U2. What is the optimal split?
It doesn't matter.
So in the middle.
How does it matter whether I do in the middle, whether I do 1 n minus 1, half half? How does it matter?
It doesn't matter.
You can always show that in the worst case, you will have to see all the elements. So it does not matter where you split it. Is it clear to everybody that it does not matter where you split it? Jogu, Bhanu, Teja?
Yes, sir.
Are you clear? It does not matter where you split it?
Yes, sir.
Okay. Anybody else has any point? Now let me modify the question. I have to search U and V. And I want to find out, so U is equal to U1, U2, UN, and V is equal to V1, V2, Vm. And I want to find out which elements of V are in U. Which problem is this?
The intersection problem?
Set intersection problem. It is the set intersection problem. How will I solve this problem?
So for every element of V, we can check in U.
One by one. Correct. No,
So,
yeah, recursive definition.
So recursively, we could keep on splitting U while keeping V as the same.
Correct.
And then. So then the recomposition would be unioning all the results.
Correct. But then, interesting. Can anybody tell me, what is the most interesting part of this recompositioning and how one solution will affect part of another solution?
Sorry, sir, could you repeat?
See, what you are saying is that you will break U to U1 and U2. You are saying you will break U1V and U2V, isn't it?
Yes, sir.
Is it okay with everybody? U1V, U2V? Sai
Yes.
Sarath?
Yes, sir, it's okay, sir.
Now, and whatever you get from here, if you get W1 and you get W2, you are going to do W is going to be equal to W1 union W2. Correct? That's what you said, Ishan?
Yes, sir. Yes, sir.
Now, what improvements will come in the algorithm? I won't do it for you. I'm asking you.
Sir, if the elements in U are not unique, then we might end up finding one element in both U1 and U2. That is also there in V.
So that union should take care. But when you are doing this somewhere here, now here you have found some Vi is an element of that U dash there, current U dashed. Okay, you have found Vi is an element of the U here. Because you have taken V on both sides, you are going to spend enormous effort searching on V for a V that has already been found. Alapan?
Yes, sir.
Ritam?
Yes, sir. So like we have to eliminate this V1 from the other one, then maybe something like we can.
So this is all part of what? I've given you a very simple problem, right? And later you will see that set, union, intersection, union, find, intersection of a set are very standard, very famous advanced data structuring problems. Jyotiraditya Aryan, are you with us in the class? Karthik Narayan Sahu?
Yes, sir, I'm here.
Have you understood that if I find some vi already in u at one branch of the recursion. On the other branch, since I have not split v, I will be still trying to search for it, so I have to remove that.
Yes, sir.
Good, good. Now I make a slight variation. I tell you that u and v are numbers, integers. That means they can be ordered in some way, whether they are integers or character strings or whatever. Let us take for the time being that u and v are integers. Then
So after ordering, we could split V into two parts, and taking the middle element of V, we can now split U into two parts and only compare the lesser sets with the lesser sets and the greater sets with the greater sets.
But they are not given to you in an ordered fashion. They are given to you in an unordered fashion.
Yes, sir, after sorting, that is.
No, but how did you decide that sorting will be more efficient than doing something else? You came to the conclusion, no? That sorting will be most efficient. Suppose I give you that V is a single element. Okay, so I tell you that U is an unordered set of numbers and V is a single element. Would you still do sorting?
No, sir.
No, sir.
Then don't jump to conclusions. Druhin Abrol, are you with us? Druhin Abrol, are you with us? Navam Singla, are you with us? Did you understand what is, can you repeat what is being discussed?
Yes, sir. We are discussing that there is a another set of U and V. We have to we have to search that V is in U or not.
Yeah, and it's a set of numbers.
Yes, sir.
And somebody suggested that we sort U and V and then do it.
Yes.
I said, how did you come to the conclusion that sorting U and V is the best thing to do? Suppose I took a case where V is a single element.
Yes, sir.
And U is a set of 500 elements or n elements. Then why should I sort U? Sorting takes so much time.
Yeah, we can solve it by using recursion. We have discussed.
Correct. So the question here is that the decision depends on many things, including the size of V and U. So I'll leave it to you to think about what is the best way to do it. Now let us say that I have to solve an ordered set of numbers. That means I have to search ordered set where U is ordered and I have to search for an element V. Already ordered.
So we can divide the U and check like in the middle part, and we can check
why middle? Why middle?
Then we can divide we can check in one part of the array.
Again, why did you make it middle? Why not 1/4, 3/4?
So maybe because it's like an educated guess, sir. Like middle seems more probable, and if not, then we can go.
We are doing algorithm design. So, what is your recursive definition? What is your recursive definition? Your recursive definition is that I have L and I have to search for an element X. I will split L into
I first found the middle part and then we check if
No,
x
no.
is
Why did I choose middle? Why didn't I choose the first element? Why didn't I choose the last element? Why didn't I choose 1/3 of the element? Why did you suddenly come to middle?
So I can always eliminate half of the list.
So
like
what?
if we divide in 1/3 and 2/3, then might be my key value is in 2/3 part, so I have to traverse the extra elements.
So like
Yeah.
That
if we
depends
split
on
at
the
the
problem.
middle, then we can ensure that in the like at max, like in the worst case, we'll have to scan the like we can reject most part of the array.
So your first point is that since it is ordered, all right, you have to search for an element X. So the first thing is you will arbitrarily choose. So if L is S1 to Sn, you will choose an arbitrary Si. We'll find out whether middle, 1/3, 1/4, n minus 1, which is the best. That is our algorithmic method, no? Our choice. Our decision making choice is like that. Kompella Lakshman Pradeep. What is your full name? Kashyap. Yeah.
Yes,
Are you with us?
yes, sir.
That I choose a particular element Si. I check if Si is X. If Si is X, my problem is solved. And because the list L is ordered, if Si is less than X, I have to look at the list beyond Si. If Si is greater than X, then I have to look at the list
To the left.
to the left of Si. My question is, what is the choice of I? People have said that I do it in the middle. But if I write the recursive equation, it becomes like this. Ti minus 1 plus T this plus 1 comparison, and it will be the largest of the left side or the right side. Yes or no?
Yes, sir.
It will be the largest of the left side or the right side. So now I have to open up the recursion tree. And when I open up the recursion tree, what does it become? If I did 1/3, 2/3, then it would go like this. And something like this. So my complexity, which is the max of T I minus 1, T n minus I plus 1, plus 1, this max in the recursion tree is reflected in what?
So height.
Height of the recursion tree. And the height of the recursion tree will be minimized when I is equal to
N by 2.
n by 2. Have you all got it now?
Yes, sir.
Yes, sir.
Yes.
Now suppose I had taken 1/3 and 2/3. What would my complexity become? Tn is equal to
T of 2 by 3
plus 1. What is the asymptotic complexity of this? My master theorem
order
or
of
whatever theorem. If I do Tn is equal to Tn by 2 plus 1, it becomes what? Order?
N log n.
N log n.
Log n log n.
If I do this, what will it become? Open it up and see.
Log of 3 by base of 3 by 2.
Correct. Is everybody with me on this?
Yes, sir.
Yes, sir.
So now log of this, if you take both to some to us, one of the logs is the constant of the other log, isn't it?
Yes.
So they are of the same asymptotic complexity. Whether I do 1/3, 2/3, 1/10, 9/10, or half-half, in terms of asymptotic complexity, all are log n. But in terms of exact complexity, half-half is better. Now is it clear, Sai Sarath?
Yes, sir.
Yes, sir.
So always explore the other unknown things so that you can see whether you have missed something or not. Even if half-half is the best you know, just this analysis yielded us some more insights, didn't it?
Yes, sir.
Yes, sir.
So that is important. Now let us come to the next question of search ordered UV, where U is ordered, V is ordered. How will you recursively decompose this problem? What is the optimal decomposition point, etc., etc., etc.
So assuming that U is the larger set and V is the smaller set, can we follow the method I suggested earlier?
What
That
did
is,
you
we find
suggest?
the middle point of U,
Hmm.
and we search. We find where that middle point splits V into two halves, and then we search the half of V which is lesser than the midpoint of U with the first half of U, and search the remaining part of V with the remaining part of U.
So generalize it, generalize it, generalize.
We can just like check the search the first element of V in U, and then um, we know that the second element will be in one of the, like if we if we have found the location of the first element, then we know that the second element will be in one of the hubs, not like depending on which order, in which order the array is sorted.
You all are all choosing. You all are all
Hello,
choosing a
sir.
specific algorithm.
Sir,
We have to generate a recursive definition based on which we will generate the algorithm. One
hello,
of
sir.
you split it into half-half and then started taking a decision that this is the best. The other said that I will take one at a time, and based on whatever I take, the other part of the list will be broken down. Now somebody else is giving another solution. Let us hear that solution.
Yes, sir.
we can just compare ui to vi, that is any random element from u to any random element from v, and then if ui is greater than that vi, that particular vi, then from vi onwards we compare we recall the function on vi and the and ui plus 1 to u final, and this is one recursion, and the other one is we call on uh, first element of u to ui and first element of v to vi minus 1.
Good, good, good. Anybody else has anything else to suggest? Let's write it down here. We had u and we had v. We had v, and both are ordered sets. Let us assume integers. Now, Apurv, tell us your solution.
So we compare ui to vi, any random ui to vi, and if for case 1, if ui is greater than vi, then we recursively
Random.
call.
So you will generate a random number and do it, or
No,
what will
so you said that we'll decide which number to generate, which
so
number to test later.
yeah,
So
okay.
for now, let's just call it ui and vi.
So you are saying I will compare
ui to vi.
ui and vj.
Sorry, vj. And
based on this, I will
you
split and split u and v, isn't it?
Yes, sir.
Has everybody understood what he is trying to do?
Yes, sir.
Yes, sir.
Sir, please explain again, sir.
He's saying you will choose some ui and you will choose some vj and compare them. What can be the result? ui can be equal to vj, ui can be less than vj, ui can be greater than vj. Got it?
Yes, sir.
Now, suppose ui is less than vj. Then what will you do?
Hello.
Bolo.
If ui is less than vj, then we can compare. We can split ui into u1 to ui and ui plus 1 to un, and we can split v into v1 to vj minus 1 and vj to vn, and we can recursively compare them.
What? Which will you have to compare? You have found ui is less than vj. So you will find out u1. You will find out a set u1 which is from u1 to u I or I minus 1?
To ui.
You will find u2 which is ui plus 1. Let us assume all are unique for the time being. And you will split v1 to
v1 to vj minus 1.
And v2 you will create as vj to vm. And what calls will you make?
v1 u1 and u1 v1 and u2 v2.
Is that sufficient? Is it? Now my question is, you will call on u1 v1 and u2 v2. Are you missing anything?
Yes, so that is the problem. Like if u1 is let's say 10 and vj is 6, Then if we compare 1 to 6 with 1 to 10, and we compare the 7th to any number with 10th to then we're missing the 7.
Apurv, got it?
Yes, sir, I got it.
So I could not hear it. Alapan, could you please repeat?
See, look at it. Look at this. Alapan, tell us your example.
Like
suppose he says, suppose U1 is 7, right? What is U1? 7 or 10 or what?
U1 is 10 and VJ is 7.
U1 is equal to 10. UI or U1? U1.
UI. Let's say 1
UI
to
is
n.
10
1
and
to n and 1
VJ
to n.
is.
VJ is 7.
But then this condition is not satisfied.
Okay. Then UI
Let us
is
take
10.
17.
Yes.
Let us take this one is UI is 10 and VJ is 17. Now, if you split U1 to all elements up to 10 and VJ to all elements before 17, the element before 17 could have been 16. Ishan.
Yes, sir.
And that 16 would have been in U2. So
that 16 would have been in V2. If it would have been better if it was in V2.
No, for the time being, we don't know. No? We don't know what is before 17 in V.
Yes, sir.
So that is why this split will not work. Just doing these two sub-problems will not work. That is what I'm saying. That is what Alapan is trying to say.
No, sir.
That if I break it up into two sub-problems, U1, V1 and U2, V2, I may not get the answer.
No, sir. I don't understand why that will not give us the answer.
Okay.
Because we know for a fact that.
Okay. I'll give you an example. Take U is equal to 1, 10, and 16, and V is equal to 1, 10, 16. V is equal to 17, 16, and 25. And I have compared these two. Will I ever find?
Okay, sir.
Alapan, this is what you're saying, right?
Yes, sir.
Apurv, you got it now?
Yes, sir, I got it. I'm thinking about it.
So the question is, what is the recursive definition?
So we should split where we find the element of V in U, or at least where the crossover happens.
Correct. So your definition is not doing this. Your definition is to select an element of V, find where it occurs in U, and then do whatever you want to do, right?
Yes, sir.
Not an arbitrary comparison like this. Because an arbitrary comparison like this does not help me reduce the problem. That is what has now made Apurv think. So I will not solve this problem for you all. But if anybody has a doubt now about how to solve an ordered list of two sets, U and V, and how to find out how many elements, which elements of V are in U, which is equivalent to finding the intersection of two ordered sets. Who has not understood what we are trying to do and why this current definition did not work? Please feel free to tell us.
Sir,
Yes.
can we compare on the basis of VM? Like first search where is VM in U and split on the basis of that.
Exactly. That is exactly what Rudrajyoti is also saying. That choose some VI and then split U based on where this VI occurs in U, if at all. That means what Rudrajyoti is saying is what you are also saying, is that I will choose a particular VI, and for that VI I will find where it occurs in U, if at all, and then split U. Is that what you're saying?
Yes, sir. I mean, I didn't generalize it much. I mean, I wanted to split on the basis of VM and next on the before element.
Generalize it.
Okay, sir.
Generalize it. Then only we will get an answer. Generalize it. Anybody else has any other thoughts or suggestions? Very good. Anybody else has any other thoughts or suggestions?
Sir, I want to add just one thing. When we are comparing first element of V in U1, then I'm just suggesting that why not we compare the last element also and split that set.
Right. So my question is, we could compare any element and split the set. Which element to choose, that we'll decide. But
Okay,
what your classmate just mentioned, she, Lalita, is that how you are called, Lalita Madhuri?
Yes, sir. Lalita Madhuri.
Lalita Madhuri just said that I will choose an element. She also wanted to choose a particular element, VM, but I suggested that you choose an arbitrary element VI, find its location, its appropriate position in U, because U is ordered, and then split U and V. Now, which VI to choose, we will decide.
So in fact, maybe we can add one more step to it by saying that if we do not find the VI which we're looking for, we find which is the position where the VI would.
Yeah, we find its position. We find its position such that we can split the list.
Yes, sir. Yes, sir.
It may not exist. It may be there, may not be there. We just find the position where it is supposed to be there if it was there. And for that, we will do that split in the middle, which we just discussed a little while earlier. What is that method called when you split in the middle? This one, which? What is this method called where you split in the middle?
Binary search.
Binary search.
So what you're saying is that we will apply binary search by choosing an element from here, apply it there, and then try to find out. And we will see that these two sorted lists, when I want to perform their union and intersection, that problem is called what problem? When I want to find their union, it is called the merge problem. when I want to find their intersection, which we are trying to do now, is called another problem. We'll stop today and you can stop the recording. And you all go through this very carefully and we'll come back with searching, sorting, and several other classes of problems where this discussion on splitting, recursive definition, and optimizing the split comes up. Union problem, we just discussed intersection problem. The union problem is called the merge problem. Any other questions? Students who have class can leave. Please stop the recording.
Thank you, sir.